If you've ever looked up at the night sky and wondered whether a rock from space could end all life on Earth, you're not alone. Scientists lose sleep over that question too. And right now, in March of 2026, a groundbreaking discovery is forcing every planetary defense expert on Earth to completely rethink everything they thought was possible. We're talking about something that has never happened before in recorded human history. Something that sounds like science fiction but is absolutely verifiably real. Imagine this. A spacecraft, no bigger than a van, built by human hands, has physically changed the orbit of an asteroid around our own sun. It didn't just nudge a small rock. It altered the trajectory of an entire binary asteroid system hurling through the solar system. Let that sink in for a moment. Humanity just moved a piece of the solar system. Before we dive in, if you're passionate about space science and the stories that actually matter for the future of our species, hit that subscribe button right now and drop a like on this video. There are thousands of channels out there, but this is where the real science gets told in a way that actually keeps you awake at night. Subscribe and never miss another discovery that could change everything. Alright, buckle up. This story starts in darkness, continues through an explosion in deep space, and ends with a revelation that scientists are still struggling to fully process. Let's go back to September 2022. Picture a spacecraft the size of a small van traveling through the vast void between Mars and the Sun, alone, millions of miles from any human being, no crew, no return trip planned, and no rescue mission if something goes wrong. It was built for one single, terrifying purpose: to crash. At 14,000 miles per hour, NASA's Double Asteroid Redirection Test, commonly known as DART, slammed headfirst into an asteroid moonlet named Dimorphos. This 5-foot-wide chunk of ancient rock had been drifting through our solar system for billions of years, completely undisturbed until we decided to hit it. The mission had a clear goal: to see if a kinetic impactor, essentially a spacecraft playing cosmic billiards, could shift an asteroid's path enough to matter for planetary defense. The target wasn't random. Dimorphos orbits a larger asteroid called Didymos, a nearly half-mile wide behemoth, about 2,550 feet across. Neither Didymos nor Dimorphos was on a collision course with Earth. They were chosen precisely because they were safe, a perfect test subject in the vastness of space. The experiment criteria for calling DART a success were modest. If the mission changed Dimorphos' orbital period around Didymos by just 73 seconds less than 2 minutes, NASA would declare victory. That was the bar: 73 seconds. Engineers and scientists huddled around screens in mission control, watching in real time as the spacecraft hurtled toward its destiny. Then came the impact. The signal cut out. The spacecraft was gone, and for a few breathless moments, the room was silent. Then the data started coming back, and nobody quite believed what they were seeing. DART didn't just meet the target. It didn't come in slightly over expectations. It smashed the success criteria into debris. The orbital period of Dimorphos around Didymos shrunk not by 73 seconds, but by an astonishing 33 minutes, nearly 30 times the required change. Scientists stared at the numbers and asked the same question again and again. How is that even possible? The answer came from the physics of the crash itself. When DART hit Dimorphos at 14,000 miles per hour, it didn't just push the asteroid, as you might imagine. The collision was far more violent. Dimorphos isn't a solid rock. It's what planetary scientists call a rubble pile. It's a loose collection of boulders and gravel, barely held together by gravity, like a giant cosmic beanbag. When DART punched into it, the impact didn't just nudge the rock, it detonated it. Thousands of tons of rocky debris exploded outward in a massive spray, hurtling into space at high velocity. That eruption of material acted like a rocket exhaust, pointing in the opposite direction. The force of that exhaust pushed Dimorphos far harder than any spacecraft ever could by itself. Scientists measured this effect using something called the momentum enhancement factor. If DART's impact had simply been brute force from the spacecraft, the factor would have been 1. Instead, the debris explosion roughly doubled the effective punch. The momentum enhancement factor was approximately 2, meaning the explosion made the collision twice as powerful as the hardware alone. In the words of one scientist at Harvard, it was an absolute sucker punch from 14,000 miles per hour. But here's where the story gets even more interesting, because the full extent of what DART accomplished has only just been revealed. On March 6, 2026, a new study was published in Science Advances, led by Rahil Makadia from the University of Illinois Urbana-Champaign and co-lead Steve Chesley, a senior research scientist at NASA's Jet Propulsion Laboratory. The paper contained a finding so extraordinary that it sounds impossible, yet here we are. When DART hit Dimorphos and Dimorphos recoiled, that recoil gave a gravitational shove to Didymos, the larger asteroid in the binary system. Remember, this is a binary system. Both asteroids share a gravitational center of mass, locked in an eternal dance around each other as they travel through the solar system. When you push the smaller partner in a gravitational dance, the larger partner feels it too. And Didymos, all 2,550 feet of it, 200 times more massive than Dimorphos, was tugged ever so slightly out of its existing solar orbit. For the first time in recorded history, a human-made object changed the path of a celestial body around the Sunday. Read those words again. Let them land. Think about where you were on September 26th, 2022. Whatever you were doing that day, at the same time, a van-sized machine was flying through deep space at 14,000 miles per hour, built for the sole purpose of destroying itself against an asteroid. And this week, scientists confirmed the full extent of what that sacrifice actually achieved. You are alive at the exact moment this species proved it can protect itself. That is not a small thing. The 770-day orbital period of the Didymos system around the Sun changed by just 0.15 seconds. The speed of the system changed by a mere 11.7 microns per second, that's about 1.7 inches. For comparison, a garden snail moves about 1,000 times faster. The change is so microscopic that it seems it shouldn't matter at all. But according to the researchers, over time, even a deviation this small can compound into something significant. Over time, such a small change in an asteroid's motion can make the difference between a hazardous object hitting or missing our planet. Rahil Makadia, in the study, wrote, "The displacement over a full year amounts to roughly the height of the Eiffel Tower, tiny today, enormous across decades." Thomas Statler, the lead scientist for solar system small bodies at NASA headquarters in Washington, called it a validation of everything planetary defense scientists have been working toward. "This is a tiny change to the orbit," Statler said, "but given enough time, even a tiny change can grow to a significant deflection." The team's incredibly precise measurement validates kinetic impact as a technique for defending Earth against asteroid hazards. And that's the terrifying beauty of all of this. The universe operates on timescales that make human history look like a blink of an eye. An asteroid that grazes past Earth on one orbit might be perfectly safe for 100 years. But then, a tiny perturbation built up over decades shifts it 3 seconds earlier, and suddenly that near miss becomes a direct hit. This is why planetary defense scientists obsess over the tiniest possible changes. This is why they care about millions of a mile per hour. Now, let me stop here for a moment, because I want you to fully appreciate how insanely difficult it was to measure this change. We're talking about detecting a shift of 22 millionths of a mile in the speed of a rock that's 7 million miles away. How do you even do that? How do you measure something that small from Earth with the noise of the universe all around you? The team used a technique called stellar occultation. It sounds poetic, and honestly, it is. An occultation happens when an asteroid passes in front of a distant star, blocking its light for a brief fraction of a second. By measuring exactly how long the starlight blinks out, and from multiple observation points scattered across Earth, astronomers can calculate the asteroid's speed, position, and even its shape with extraordinary precision. But executing this is brutally difficult. You need the right telescopes in the right locations on the right night, pointed at the right star at the right exact moment. Clouds can ruin everything. Equipment failures can erase months of planning, and the asteroid's shadow might fall on a remote mountain range in the middle of nowhere. The team relied on dozens of volunteer astronomers scattered around the world. Citizen scientists, amateur observers with dedication and passion, who recorded 22 successful stellar occultations between October 2022 and March 2025. More than 2 years of painstaking collaboration, all to nail down a measurement that most people would say shouldn't even be possible. Study co-lead Steve Chesley summed it up perfectly. This work is highly weather-dependent and often requires travel to remote regions with no guarantee of success. This result would not have been possible without the dedication of dozens of volunteer occultation observers around the world. 2 years, 22 occultations, dozens of volunteers chasing starlight in the dark, all to measure a change smaller than a garden snail's sneeze, and they nailed it. The measurement is real, the orbit change is real, and the precision with which we proved it may be just as extraordinary as the achievement itself. Now stay with me here, because this next part is something almost no mainstream outlet has highlighted, and it reframes everything about what this discovery actually means. Before DART launched, scientists had to think through every worst-case scenario. One of those scenarios was terrifying. What if DART hits Dimorphos, and Dimorphos shoves Didymos, and Didymos ends up on a collision course with Earth? What if we accidentally redirected a 2,550-foot asteroid toward our own planet? Rahil Makadia was one of the scientists who ran those numbers before launch. What if this experiment puts the Didymos system on a collision course with Earth? That was obviously not desirable. So they looked into it. The conclusion back then was that the impact on Dimorphos would have no detectable effect on Didymos. It was deemed safe. Ironically, the new study proves that conclusion was wrong. DART was so powerful, it did move Didymos. It moved the entire system. Nobody predicted that. But the crucial follow-up, they ran the real numbers, and Didymos is still not a threat. Earth is safe. We're safe from Didymos impacting the Earth, Makadia confirmed. But this overperformance has huge implications for planetary defense going forward. What the mission revealed is that rubble pile asteroids, loose fragmented collections of rock like Dimorphos, are incredibly responsive to impacts. Hit them with a spacecraft, and they don't just get pushed. They explode, they shed material, they react like a liquid. In fact, after DART's impact, Dimorphos actually changed shape, literally reshaped by the collision, behaving more like a fluid than a rigid rock. The density measurements that came out of this new study tell the story clearly. Dimorphos has a density only slightly higher than water. That's astonishingly low for a rock. Dimorphos is not a mountain. It's a pile of rubble masquerading as a mountain. Didymos, by contrast, has a much higher density, more like an actual solid rock. The difference matters enormously if you're ever trying to defend Earth. Consider this scenario. A rubble pile asteroid is detected on a collision course with Earth. You send a DART-style spacecraft to deflect it. But if you hit too hard, you don't just push it, you shatter it. Instead of deflecting one asteroid, you've created a shotgun blast of fragments, all still heading toward Earth. You've turned one bullet into 100 pellets. That's worse. Much, much worse. For a dense, solid asteroid like Didymos, the problem is the opposite. The impact barely moves it because there's no exploding debris cloud to amplify the force. You might need multiple spacecraft, and scientists have actually discussed this, a nuclear device. A carefully calculated nuclear detonation near a solid asteroid can vaporize the surface material, creating the same kind of exhaust thrust without fragmenting the core. These aren't science fiction options. These are real tools being studied and debated in planetary defense circles right now. The discovery of how to handle both types of asteroids, rubble piles, versus solid rocks is one of DART's most lasting contributions to the field. The mission wasn't just a one-time test. It was a data factory, and the data is still being analyzed, still yielding surprises, still rewriting assumptions even 3.5 years after the spacecraft ceased to exist. And here is where the story shifts from past achievement to future consequence, because what's coming in the next 12 months may be even more revealing than DART itself. Later this year, in 2026, the European Space Agency's Hera spacecraft is scheduled to arrive at Dimorphos. Hera's mission is forensic. It's going to survey the wreckage DART left behind, mapping the crater, analyzing the changed shape of the asteroid, and measuring densities with its own instruments independently. Where DART was the wrecking ball, Hera is the investigator walking the crime scene with a flashlight and a notebook. Together, DART and Hera form a complete scientific picture of what happens when humanity punches back against the solar system. While Hera is doing its forensic work, NASA is busy building something even more ambitious. The Near-Earth Object Surveyor, or NEO Surveyor, is the first space telescope ever built specifically for planetary defense. Unlike ground-based observatories, which are constantly battling weather, atmospheric distortion, and the blinding glare of the sun, NEO Surveyor will operate in space, scanning regions of the sky where the most dangerous asteroids hide dark asteroids, comets that barely reflect any visible light, objects that today could be completely invisible to us until they're dangerously close. The timelines of planetary defense are long. The distances are incomprehensible. The stakes are existential. And yet, we are not helpless. We have the proof. A van-sized machine changed the orbit of an entire binary asteroid system around the Sunday. Think about what that means in the context of human civilization. For all of recorded history, every empire that rose and fell, every war ever fought, we were essentially passengers. Earth moved where gravity told it to move. Asteroids flew where orbital mechanics dictated. There was nothing we could do if the solar system decided to throw a rock at us. September 26, 2022 changed that, and March 6, 2026 confirmed it beyond any shadow of a doubt. We are no longer just passengers. For the very first time, we are navigators. Andy Rifkin, a planetary astronomer at Johns Hopkins Applied Physics Laboratory and one of the co-authors of the new study, put it with beautifully simple clarity. By hitting the moon as hard as we did, we also moved the giant thing next to it a little bit, 1.7 inches per hour, the Eiffel Tower per year. The numbers are small, the implications are infinite. What comes next matters enormously. The solar system holds hundreds of millions of near-Earth objects, many unknown, many dark, invisible to our telescopes until they're dangerously close. NEO Surveyor will find them, Hera's forensic data will sharpen our models, and missions that haven't even been designed yet will use everything DART taught us. There will be more, smarter, more targeted, more powerful missions operating so far in advance that an asteroid threatening Earth decades from now can be quietly, invisibly redirected before anyone ever feels the danger. That is the future DART made possible. That is what March 2026 confirmed. The universe has been throwing rocks at planets since the beginning of time. Dinosaurs couldn't do anything about it, but we can. We are the species that looked at the same threat that ended 75% of all life on Earth 66 million years ago, built a machine, flew it to a specific rock millions of miles away, and moved it. We moved an asteroid's orbit around the Sunday. If that doesn't make you want to be alive in this era of science and exploration, I don't know what will. This is the real story of 2026. Not the political noise, not the economic uncertainty, not the endless scroll of daily anxiety. The real story is that humanity, for the first time ever, is a spacefaring civilization with the ability to protect its own planet. The real story is written in 22 stellar occultations, in 1.7 inches per hour, in 33 minutes of orbital change, and in a tiny spacecraft that vaporized itself against an ancient rock to prove that everything we believed was hopeless about asteroid impacts was wrong. We are not helpless. We are the species that punched an asteroid and moved the solar system, and we are just getting started. If this video blew your mind the way it blew mine when I first read the study, please hit that like button right now. It takes 2 seconds, and it tells the algorithm that stories like this deserve to be seen. And if you want to be here for the next discovery, the next time science rewrites everything we thought we knew, subscribe to this channel, turn on the notifications, because there is so much more coming. From Hera's arrival at Dimorphos, from Neo Surveyor, from missions we haven't even announced yet, the golden age of planetary defense is not some distant future promise. It is happening right now, and you are watching it unfold in real time. Thank you for being here. See you in the next one. Stay curious, stay amazed, and remember this. In every era of human history, people assumed they were helpless against the universe. Every single time, they were wrong. We are not the last generation to face this sky. We are the first generation that actually knows how to fight back.